For years, large language models have been hailed as powerful but inscrutable black boxes, performing amazing feats without revealing their inner workings. Now, a rapidly evolving frontier called mechanistic interpretability seeks to peel back these layers, dissecting the precise computational mechanisms that drive an LLM's behavior. This goes far beyond superficial explainability, aiming to reverse engineer the actual algorithms and representations learned deep within the model's neural network. Understanding these internal processes is crucial for building truly safe, reliable, and aligned AI systems that we can trust in high-stakes applications. A core concept in this domain is the identification of modular circuits, defined as task-agnostic, reusable functional units within an LLM. These are small computational subgraphs that perform consistent operations across diverse language tasks, acting like specialized mini-algorithms. This approach marks a significant advancement over earlier task-specific circuit analyses, which often lack generalizability across different contexts. By identifying these modular components, researchers can begin to map the underlying architecture of intelligence that LLMs develop. One major challenge in LLM interpretability is polysemanticity, where a single neuron can respond to multiple, often unrelated, concepts simultaneously. This makes it incredibly difficult to isolate and understand what specific function a neuron is performing, obscuring the model's logic. To address this, sparse autoencoders, or SAEs, have emerged as a powerful tool to disentangle these complex features into more interpretable, monosemantic components. SAEs achieve this by learning a sparse representation of hidden layer activations, employing a sparsity penalty during training to encourage distinct and individually meaningful features. The actual mechanism behind mechanistic interpretability involves a blend of advanced neural network techniques and rigorous causal inference. Researchers systematically test hypotheses about the causal effects of identified circuits or features on the model's output using techniques like causal intervention. Activation patching involves swapping specific activations between different model runs to pinpoint exactly which parts of the circuit are critical for a given behavior. Similarly, neuron ablation involves temporarily disabling individual neurons or entire circuits to observe how their removal impacts the model's performance and output. Frameworks like ModCirc leverage reinforcement learning-based graph neural partitioning to automatically discover these elusive modular circuits. This advanced partitioning method helps identify coherent, functional units within the vast and complex LLM architecture. Other work, such as an interpretable automated mechanism design framework, uses LLMs themselves to generate and evolve heuristic mechanisms in code. This framework includes a fixing process to ensure design criteria are met, allowing for the creation of more interpretable and robust solutions by the AI. The pursuit of mechanistic interpretability is foundational for building genuinely trustworthy AI systems across all sectors. It allows developers and regulators to finally understand why an LLM makes a particular decision, not just what it decided. This enables targeted debugging of undesirable behaviors like hallucinations, bias, or unsafe outputs, particularly vital in high-stakes applications. Imagine applying this in medical diagnostics, where understanding an AI's reasoning could be the difference between life and death. Mechanistic interpretability is also crucial for ensuring regulatory compliance, especially with emerging frameworks like the EU AI Act. These regulations increasingly demand greater transparency and accountability in AI systems, pushing for a deeper understanding of their inner workings. By uncovering the underlying computational graph, researchers can work towards aligning AI systems more precisely with human intentions and values. This alignment is paramount for preventing unintended consequences as AI capabilities continue to expand and integrate into our lives. While progress in mechanistic interpretability is rapid on smaller models, the sheer size and complexity of cutting-edge LLMs present enormous challenges. Comprehensively mapping and understanding every circuit within a multi-trillion parameter model is a monumental task that quickly overwhelms current methods. The computational resources and human effort required to achieve fine-grained understanding escalate exponentially with model size. This raises a significant caveat. Will MI truly scale to provide a complete understanding of frontier LLMs, or will it remain a localized tool? Further complicating scalability is the superposition hypothesis, which posits that neural networks store more features than they have physical neurons. They achieve this efficiency by representing multiple concepts in overlapping combinations within the same neurons, leading to intense polysemanticity. This means a single neuron might be involved in detecting cat ears and car wheels simultaneously, making its individual interpretation incredibly challenging. The inherent complexity of such compressed representations makes it hard to isolate and reliably interpret these polysemantic neurons, even with advanced tools like SAEs. So, the open question remains, can mechanistic interpretability techniques truly scale to provide a complete, fine-grained understanding of frontier LLMs? Or will it remain a powerful but localized tool, offering only partial insights into these increasingly autonomous and opaque systems? The quest to understand the algorithmic core of AI continues, promising a future where intelligence is not just powerful, but also profoundly transparent.